So again, I will spend one more lecture on the examples on the second unit. The first example today I will consider this one. The gun of mass m fires a cell of mass m horizontally, and the energy of explosion is such as would be sufficient to project the shell vertically to a height h, so that the velocity of recoil is this square root of 2 times m square gh upon capital M into small m plus m. So this is the velocity of the recoil. So we have here gun whose mass is capital M, and this gun fires a shell whose mass is denoted by small m and horizontally. So direction. So if the gun is, say, at this, and if the sail, so sail moves in this direction horizontally, okay, and then what will be the velocity of the recoil? So here, see, what is recoil? So this sail moves maybe like this, okay. So what is the velocity of this recoil, you can think? Or see, you might have seen some explosion phenomena. So what you will observe? So there is an explosion at this point, say, right? And we have a cloud like this, which spreads in this way, like this, in the sky. Okay, so you can think of this as a recoil, as far as that explosion phenomena is concerned. Okay, so we have such kind of problem. So let us see how to prove, or how to see that the velocity of that recoil is given by this formula, you can say, which is the square root of this quantity. Okay, so let us denote capital Phi is the velocity of recoil of the gun, then by the principle of linear momentum. What is the principle of linear momentum? Momentum before impact is same as momentum after impact. That is what the principle of linear momentum is. So momentum before impact means before firing the shell, and after impact means there then explosion took place. So what will be the momentum in that case? And therefore we have, as we denote phi is the velocity of recoil, so it is nothing but capital M. M is the mass of gun, and this is equal to M into phi, and here small m is the mass of cell. So this is, and velocity is small p, therefore it is m into. So we denote this expression by 1. Okay. By this is written by principle of linear momentum. And when the cell leaves the gun, or there is a fire phenomena, its velocity at the muzzle b, we denote it by u, which is sufficient to project the cell vertically, so that cell projects in this direction vertically, which height is denoted as h. And then therefore here square of u, or square of the velocity, is equal to 2 times g into h, where h is the height of the projection and g is the acceleration due to gravity. Now, what is the principle of conservation of energy that we will use here? So, by principle of conservation of energy, you try to remember 1 and 2, equation 1 and 2. So, principle of conservation of energy says potential energy plus kinetic energy is the work done. Potential energy, I will write here because in equation 3 you cannot see equation 3. So I will write in short. Potential energy PE, and I will write kinetic energy as KE. So sum of potential energy and kinetic energy is nothing but work done by the force or work done due to the impulse. And therefore, using this, we can have, we call this as third expression, and we just put the values of work done and this. So half into, this is the kinetic energy, m into v square, where m is the mass of the gun. And this is half into m, capital M upon m square v square. So this is nothing but the ratio of two masses. This is the acceleration due to gravity, you can say g. So mass of the cell m into g square into v square. And so this is kinetic energy, this is potential energy, and this is the work done. So half into 2 times mgh. And if you simplify further, half is common, right? So it cancels, and what remains only mv square plus, this is, if you take the square of this, it is capital M square upon small m square. And again we are multiplying by m, so that will vanish. One m vanish from denominator. And what we have, m square upon v. And this is v square is equal to 2 times mgh. So h is the height of the projection, g is the acceleration due to gravity, and this small m is the mass of the cell. And if you simplify further this left hand side, so you can take m phi square common. So if you take m phi square common, this is 1, right? So I will write here 1 m phi square common. So m into phi square, right? And you are taking common, and therefore we write this as 1 plus what remains, only small capital M divided by small m. So this is the left hand side. Right hand side is 2mgs, and you take LCM in this bracket. So what is LCM? LCM will be m that I have here, and numerator is m, small m plus capital M. This is 2 times mgh. And from this you can find the value of phi square. So phi square is what? So 2, so this m multiplied by m will be m square gh, right? And what is the denominator? Capital M into small m plus m. This is the denominator. And if you take the square root, so I forget to write square root here. So this is like this. Okay. Or instead of this, you can write this in this way, to the power half. So this is what we have to show. So this is the velocity like this. Now you can, this is a general result. You can take some values to small m. So I will take that here. If I have, I will take the values of height is say 10 meter, or I will not take the units. So you can take, this is height is m in meters. Okay. Mass of the shell, say 2 or 20 gram I can take. So you should take all units in one system, either CGS or MPS. Right? Then capital M, mass of the gun is say 10 gram also, right? We know the acceleration due to gravity. So this is what 9.8, or you can take 980. So I will take this as meter per second square. So if you take these values, then what will be the velocity? So for that you just use this formula. So just put the values of small m, g, h. So what is velocity? Velocity is equal to 2 times small m is 20 square. So it is 2 square of 20 is 400, right? Into g, value of g is 9.8, and into value of h, height is how much? It is 10 meter, right? Divided by capital M is 10, and addition of these two masses is 10 plus 20. I will write direct 30, right? And if we simplify further, this is equal to, this is equal to, so this is 980, this is 2, 2 times 4, 800 multiplied by, or 800 multiplied by 9, 9.8 is 98, divided by, this is 300. So you calculate this number. So that is the velocity. Okay. Next example. A cell of mass m, small m1 plus m2 is fired with a given velocity in a given direction. So there is no restriction on direction over here. At the highest point of the path, the cell explodes into two portions of masses m1 and m. So what is what we have here after a certain height? So see, if you take a cell, I will take the cell like whose mass is m1 plus m, right? And suppose when it fires, it has some velocity along this direction. It fires along this direction, right? So this is the direction of fire, and it reaches at this highest point, so that the height, it has some highest point. So let us denote that height by this. And after this height, it gets explodes. So explosion took place, and Then explosion it in two parts. So this is whose mass is m1, and other part is this whose mass is m. That is, and the explosion produces additional kinetic energy. So this explosion produce additional kinetic energy that is denoted by a capital E, and the portions separate out in a horizontal direction, so that the portions strike the ground at a distance. So when this explosion took place, these two portions strikes the ground, means reaches the ground at distance. So that distance is given by this formula. P upon G into square root of 2 times E, where E is the kinetic energy, additional kinetic energy produced due to the explosion, 1 by M1 plus 1 by M. So how do you solve this example? Time time reached to the highest point is nothing but velocity. Velocity, time depends on the what is the velocity of that cell, and acceleration due to gravity. How much away it is from the ground. So therefore, the time is at highest point is taken as phi upon g. If u is the horizontal component of the velocity of the projection, and u1 and u2 those for fragments. Fragments means here it gets, after explosion it gets divided into two parts, or they are the components, right? So these are the projections u1 and u2. Then by principle of conservation of momentum, so here the momentum for this particle is m1 plus m2 into the velocity component, and this is m1 u1 plus m2 u2 is the momentum after explosion. So mass of this shell is m1, and its velocity is u1, and mass of this another cell is m2, it has velocity u. So this is by principle of law of conservation of, and by the law of conservation of energy, so we just find kinetic energy. So this half into mass of the particle into velocity. So you know the how to find the kinetic energy. So that is nothing but half into m into p square, where m is the mass and v is the velocity of that particle. So this is nothing but kinetic energy. So using this kinetic energy and law of conservation of energy. So what is the law of conservation of energy? The kinetic energy due to the linear momentum at initial stage is same as the sum of the kinetic energy at final stage. And therefore, you can have half m1 plus m2 u square plus e, where e is the additional kinetic energy that we are going to consider here, plus half into m1 u1 square plus half m2 u2 square. And What is the relative speed of the fragment? It is equal to difference of the two velocities. So u2 minus u1. Right? Now multiplying equation 2 by m1 plus m2 and subtracting from it the square of 1. So you will have this long expression, right? So multiply equation 2 by m1 plus m2. So it is like this. So this is equation 2. This one is. So we have to multiply by m1 plus m2 and then subtract it from 1. Right? So after multiplying m1 plus m2, m plus 1 m2, and similarly to the left hand, this right hand side, and then subtract. So this here, m1 plus m2 square, u square plus 2 times e, m1 plus m2, right? So simplify further. So this is a simple calculation. You can do it very well. And see here, finally we have this relation. 2 times E, where E is additional energy, additional kinetic energy, m1 plus m2 is equal to m1 into m2, u2 minus u1. So this is the speed, square of the speed, that is the mean. And we can calculate this speed, square of the speed, u2 minus u1 square as m1, m2. So instead of small e, we should have capital E, right? So u2 minus u1 bracket square is equal to 2e m1 plus m2 divided by m1 plus m. And this is nothing but 1 by m1 plus 1 by m. So square of the speed is equal to 2 times additional kinetic energy into sum of the reciprocals of the masses. That is what. And you take square root on both sides, we get u2 minus u1 is square root of 2e 1 upon m1 plus 1 upon m. So this is the relative speed of the component. And to reach the time to reach the ground for each is 3 upon g. And hence, therefore, the distance between their positions of striking is nothing but time into speed. And therefore, this is equal to, what is time now? Time is equal to v upon g, that we know. And you simplify further. So what is u2 minus u1? Just now here, u2 minus u1 is this value. So put that value here. V upon g as it is into square root of. So this is the distance between their positions of triangle. Okay. So again, you can assign some values to the masses m1, m2. Take some additional kinetic energy. You know the velocity of the that gun, and g is the acceleration due to gravity. So you will be able to see what is the distance between those two parts of a sail after firing process, right? Next example. Next and last example of this unit. A sail of mass m is moving with velocity v. An internal explosion generates an amount of energy E and breaks the sail into two portions whose masses are in the ratio m:1. The fragment continues to move in the original line of motion of the sail. So moving process is going on. There is no stop. Okay, so it continues. That is the assumption. Show that their velocities of first portion is p plus square root of 2m2 capital E divided by m1m, and another portion is p minus 2me m1 into E upon m2 m. So let us see how to do this, how to prove it, how to find it. So let us try to understand the problem first. See here. Suppose this is the cell that we have, okay? Whose mass is given. So that mass is, say, capital M. Mass of the cell is M. And it is moving in any direction. And its velocity is denoted by P. It is moving in any direction. Suppose it is moving in horizontal direction, right? And internal explosion generates. There is an internal explosion, not external, right? So due to this internal explosion, this generates the potential energy, not potential energy, amount of energy capital. And this cell breaks into two parts. So first part is, say, this one. And another part is, say, okay, whose mass is, their masses are proportional, M1 and this fragment continues to move in original line of motion of the cell. So what are their velocities? It is also moving in the same direction. Second portion also moves in same direction. That is the assumption. And then we have to show that the velocity is velocity of first portion. You can take this as this one, right? P1, and this is the velocity of the second portion. So this is what we are going to assume here and try to find the velocity. So I hope you understand what kind of problem you are going to solve. So let us denote capital M1 and M2 are the masses of two parts after explosion. I have shown you the two parts. So first, the first mass of the first portion is M1, mass of the second portion is M2. That we have, and therefore, as the mass of the cell, original cell is capital M, therefore, sum of these two masses will be M, right? And also we have given that these masses are in the ratio M1 is to M2, and therefore we have M1 upon M2 is equal to M2 upon M2, so that their masses are in the proportion in the ratio M is to M. And then this implies M1 upon M1. So you can write here M2 upon M2. Here is a mistake. It should be this. So this is equal to M1 plus M2, right? And M2, M1 plus M2. So this is just one of the very basic property of ratio and proportion. You know this property. If we have A divided by B is same as C upon D. So this is equal to A plus C. You can add numerators and denominators. That is what. So they are in proportional. That is what it means. B plus D. Right. So using this process, you can have M1 plus M2 divided by M1 plus M2. But what is capital M1 plus M2? From 1, it is capital M. So we have the second expression. Now let us consider the velocity of the cell before explosion is V, and after explosion the velocity of two parts is V1 and V. Okay. So we assume this and see what we have further. So by principle of conservation of linear momentum, we have this mass of the cell before explosion into velocity is equal to, this is the linear momentum after uh, explosion. First particle, first portion, second portion. This is equal to capital M into P. Right? And what is the kinetic energy before explosion? Half into mass of the particle into square of the velocity. And if E is the energy due to explosion, then the total energy at the time of explosion is just you have to add that additional energy in the earlier kinetic energy or energy at initial stage. And therefore, the total kinetic energy after the explosion is this. This is the kinetic energy uh, for the portion, say first portion, and second one is kinetic energy of the second portion whose mass is m. Right? And therefore, again by principle of energy, we have this. Yes. So this is four. We have already used this principle of energy in the previous day. Then let us do this calculation. So this is 4, equation 4. So we have to multiply this 4 by 2 times m1 plus m, and then simplify. Again, it looks, the calculation looks very complicated, but it is very simple. Just you have to multiply and arrange the things. And if you simplify further, this is 2 times em1 plus m. So we calculate this value. Right? So this is equal to m1 plus m2 into, so you just see this one, this term and this term, and get some of the terms will vanish. And this is equal to, this can be written as, so this bracket is the expansion, this is only bracket, not m1. This is the expansion of p1 minus p2. And from this is equal, finally we have this is equal to this. So from this expression you find square of the difference of two velocities, v1 minus p2. So this is 2e m1 upon m2 divided by m1, right? So what is capital M1 plus M2? This is capital M. This is from equation 1 we have, right? And take the square root. So after taking square root, we have difference of these two velocities, right? And we solve equation 2 and 3. We get this. So P1 minus P2, 2 and 3. This is third expression and second expression. So use these values and see that we have this relation. Just putting the values. So here you can take P1, value of P1 is this, P2 plus square root of this, right? And simplify. So what is P1? P1 is this. Again simplify further, this. So again for this M1 plus M2, you can write capital M, right? Write capital M for this M1 plus M. Use the equation 1 and get. So this M, 1 M vanishes with M, 1 M. 1 M2 vanishes with 1 M2. And what remains would be in the numerator 2E M2 and in the denominator M1. Yeah, M1 into M. Right? So this is equal to, now we know that the M1, M2 is same as small m1 and m2. They are in proportional, right? And therefore you can take small capital M1 as small m1 and capital M2 as small m2, and therefore this is right. So this is about the third example from unit second. So with this, now I declare that the second unit is completed. So I will conduct one unit test on each topic. So I will share the question paper on Google Classroom. You solve that question paper and submit it on the same platform, that is Google Classroom. Okay, so with this I will stop here. Next time I will continue the third unit of this paper. Okay, so with this I will stop. If you have any doubt regarding this, you can ask.